In mathematics, the Klein bottle (Klein) is an example of a non-orientable surface. It is a two-dimensional manifold against which a system for determining a normal vector cannot be consistently defined. Other related non-orientable objects include the Mobius strip and the real projective plane. Whereas the Mobius strip is a surface with boundary, a Klein bottle has no boundary. The Klein bottle was first described in 1882 by the German mathematician Felix Klein. It may have been originally named the Kleinsche Flasche and then misinterpreted as Kleinsche Flasche, which ultimately led to the adoption of this term in the German language as well. Construction. The following square is a fundamental polygon of the Klein bottle. The idea is to glue together the corresponding colored edges so that the arrows match, as in the diagrams below. Note that this is an abstract gluing in the sense that trying to realize this in 3 dimensions results in a self-intersecting Klein bottle. To construct the Klein bottle, glue the red arrows of the square together, resulting in a cylinder. To glue the ends of the cylinder together so that the arrows on the circles match, you must pass one end through the side of the cylinder. Note that this creates a circle of self-intersection. This is an immersion of the Klein bottle in 3 dimensions. This immersion is useful for visualizing many properties of the Klein bottle. For example, the Klein bottle has no boundary, where the surface stops abruptly, and it is non-orientable, as reflected in the one-sidedness of the immersion. The common physical model of a Klein bottle is a similar construction. The Science Museum in London has on display a collection of hand-blown glass Klein bottles, exhibiting many variations on this topological theme. The bottles date from 1995 and were made for the museum by Alan Bennett. The Klein bottle, proper, does not self-intersect. Nonetheless, there is a way to visualize the Klein bottle as being contained in 4 dimensions. By adding a 4th dimension to the 3-dimensional space, the self-intersection can be eliminated. Gently push a piece of the tube containing the intersection along the 4th dimension, out of the original 3-dimensional space. A useful analogy is to consider a self-intersecting curve on the plane. Self-intersections can be eliminated by lifting one strand off the plane. Suppose for clarification that we adopt time as that 4th dimension. Consider how the figure could be constructed in XYZ-T space. The accompanying illustration shows one useful evolution of the figure. At t equals 0, the wall sprouts from a bud somewhere near the intersection point. After the figure has grown for a while, the earliest section of the wall begins to recede, disappearing like the Cheshire Cat but leaving its ever-expanding smile behind. By the time the growth front gets to where the bud had been, there's nothing there to intersect and the growth completes without piercing existing structure. The 4 figure as defined cannot exist in 3 space but is easily understood in 4 space. More formally, the Klein bottle is the quotient space described as the square 0, 1 times 0, 1, with sides identified by the relations tilde for 0 y1 and tilde for 0 x1. Properties. Like the Mobius strip, the Klein bottle is a 2-dimensional manifold which is not orientable. Unlike the Mobius strip, the Klein bottle is a closed manifold, meaning it is a compact manifold without boundary. While the Mobius strip can be embedded in 3-dimensional Euclidean space R3, the Klein bottle cannot. It can be embedded in R4, however. The Klein bottle can be seen as a fiber bundle over the circle S1, with fiber S1, as follows. 1 takes the square from above to B, the total space, while the base space B is given by the unit interval in Y, modulo 1 to 0. The projection pi EB is then given by pi equals Y. The Klein bottle can be constructed by joining the edges of 2 Mobius strips together, as described in the following limerick by Leo Moser. A mathematician named Klein thought the Mobius band was divine. Said he, if you glue the edges of 2 you'll get a weird bottle like mine. The initial construction of the Klein bottle by identifying opposite edges of a square shows that the Klein bottle is a CW complex with 1 0 cell P, 2 1 cells C1, C2 and 1 2 cell D. Its Euler characteristic is therefore 1 to 2 plus 1 equals 0. The boundary homomorphism is given by D equals 2C1 and C1 equals 0, yielding the homology groups of the Klein bottle K to be H0 equals Z, H1 equals Z times and Hn equals 0 for n greater than 1. There is a 2-to-1 covering map from the torus to the Klein bottle, because two copies of the fundamental region of the Klein bottle, one being placed next to the mirror image of the other, yield a fundamental region of the torus. The universal cover of both the torus and the Klein bottle is the plane R2. The fundamental group of the Klein bottle can be determined as the group of deck transformations of the universal cover and has the presentation less than A, B. AB equals B minus 1A greater than. 6 colors suffice to color any map on the surface of a Klein bottle. This is the only exception to the Heawood conjecture, a generalization of the 4-color theorem, which would require 7. A Klein bottle is homeomorphic to the connected sum of two projective planes. It is also homeomorphic to a sphere plus 2 cross caps. When embedded in Euclidean space, the Klein bottle is one-sided. However, there are other topological 3 spaces, and in some of the non-orientable examples a Klein bottle can be embedded such that it is two-sided, though due to the nature of the space, it remains non-orientable. Dissection. Dissecting a Klein bottle into halves along its plane of symmetry results in 2 mirror image Mobius strips, i.e., one with a left-handed half-twist and the other with a right-handed half-twist. Remember that the intersection pictured isn't really there. Simple closed curves. One description of the types of simple closed curves that may appear on the surface of the Klein bottle is given by the use of the first homology group of the Klein bottle calculated with integer coefficients. This group is isomorphic to Z times Z2. Up to reversal of orientation, the only homology classes which contain simple closed curves are as follows. Up to reversal of the orientation of a simple closed curve, if it lies within one of the 2 crossgaps that make up the Klein bottle, then it is in homology class, or, if it cuts the Klein bottle into 2 Mobius strips, then it is in homology class. If it cuts the Klein bottle into an annulus, then it is in homology class, and if bounds of disk, then it is in homology class. Parameterization. The figure 8 immersion to make the figure 8, or bagel, immersion of the Klein bottle. You can start with a Mobius strip and curl it to bring the edge to the midline. Since there is only one edge, it will meet itself there, passing through the midline. It has a particularly simple parameterization as a figure 8 torus with a half twist. For 0 theta less than 2 pi, 0 v less than 2 pi and r greater than 2. In this immersion, the self-intersection circle is 0, is a geometric circle in the xy plane. The positive constant r is the radius of this circle. The parameter theta gives the angle in the xy plane, as well as the rotation of the figure 8. And v specifies the position around the 8-shaped cross-section. With the above parameterization, the cross-section is a 2-to-1 Lissajous curve. 4D non-intersecting. A non-intersecting 4D parameterization can be modeled after that of the flat torus, where r and p are constants that determine aspect ratio. Theta and v are similar to as defined above. V determines the position around the figure 8 as well as the position in the xy plane. Theta determines the rotational angle of the figure 8 as well and the position around the ZW plane. Epsilon is any small constant and epsilon sinv is a small v-dependent bump in ZW space to avoid self-intersection. The V-bump causes the self-intersecting 2D planar figure 8 to spread out into a 3D stylized potato chip or saddle shape in the XYW and XYZ space viewed edge-on. When epsilon equals 0, the self-intersection is a circle in the ZW plane less than 0, 0, cos theta, sin theta greater than 3D pinched torus, 4D Mobius tube. The pinched torus is perhaps the simplest parameterization of the Klein bottle in both 3 and 4 dimensions. It's a torus that, in 3 dimensions, flattens and passes through itself on one side. Unfortunately, in 3 dimensions this parameterization has 2 pinch points, which makes it undesirable for some applications. In 4 dimensions the Z amplitude rotates into the W amplitude and there are no self-intersections or pinch points. You can view this as a tube or cylinder that wraps around, as in a torus, but its circular cross-section flips over in 4 dimensions, presenting its backside as it reconnects, just as a Mobius strip cross-section rotates before it reconnects. The 3D orthogonal projection of this is the pinched torus shown above. Just as a Mobius strip is a subset of a solid torus, the Mobius tube is a subset of a toroidally closed sphere and a bottle shape. The parameterization of the 3-dimensional immersion of the bottle itself is much more complicated. Here is a version found by Robert Israel. For 0u less than pi and 0v less than 2 pi. Generalizations. The generalization of the Klein bottle to higher genus is given in the article on the fundamental polygon. In another order of ideas, constructing 3 manifolds, it is known that a solid Klein bottle is topologically equivalent with the Cartesian product, the Mobius strip times an interval. The solid Klein bottle is the non-orientable version of the solid torus, equivalent to Klein surface. A Klein surface is, as for Riemann surfaces, a surface with an atlas allowing the transition maps to be composed using complex conjugation. One can obtain the so-called dianalytic structure of the space.